Okay, section 7.3 is called reactive power. So here we go. Brand new concept for us. Very interesting. Something that's always been there, but because you didn't know it was there, you didn't know it existed. And this idea of reactive power, it's a new world for us. It's power that pulses and it goes in one direction and then it comes back in the other direction. And it's very interesting. And it's also something very necessary for us to be able to use things that rely on a magnetic field to operate. So let's look at a variation of the circuit that we looked at in 7.2. So here's looks very much like the circuit that we were looking at before, right? And the only thing that's different now is that we have replaced that resistor with an inductor, okay? And that inductor value is given to us as a J number, and I hope you remember that from your time in circuits where you worked with those reactances. But when we think about an inductive reactance, we think about that being a positive value. So anyway, so here we are. We have a source of AC, we have a voltage, we have current that's flowing to the device. And this now is our load, and it's totally inductive. Then as we move from that, we remember that when we talk about an inductor, this idea of Eli the Iceman, right? Eli the Iceman. The voltage will lead the current. The voltage will lead the current by 90 degrees in a purely inductive circuit. And we see that here in this phasor representation of that. And we see the voltage out in front of the current by 90 degrees, right? Represented by that. Now, what really goes on in a circuit, and we've got the waveforms drawn here. Let me erase all this, and I'm going to increase the size of this so that we can get a little better look of it. And so, again, we have voltage and current across here, right? And so I'll go with the blue. And so here is our voltage. Tracing the voltage across here. And here is the current. We'll go with green for current. And here is the current here. All right. And then just as before, we're going to plot instantaneous values by multiplying the instantaneous value of E times the instantaneous value of I to get the instantaneous power, okay? So, same thing, same concept as before, but I want you to notice, let me wipe some of this out so I think it's easier to see. I want you to notice something here. This portion of the power curve, which is the product of the voltage, instantaneous voltage and current. And, these are giving us our peak values, which is the effective times the square root of 2, effective times the square root of 2 for the current. But notice that we have just as much power above the x-axis as we have below, or maybe I should have said we have just as much power below the x-axis as we do above it. Okay, so what in the heck is going on here? All right, now if we look at a positive wave and we go back to this circuit here, if we look at a positive portion of these circuit diagrams, the power in the positive wave is the power that's delivered by the generator to the inductor. Now, also, let me point this out to you. He refers also as an inductor as a reactor, okay? And that's a common electrical term, a reactor, okay, is another term for an inductor. But the positive waves correspond to instantaneous power that's delivered by the generator to the reactor. And the negative waves, now here you go, here's this new concept here. These negative waves are indications of power that's delivered from the inductor back to the generator. So on one cycle, we give this load, react this power, and on the other end of this, that reactor or inductor is just returning that power back. The duration of each wave corresponds to a quarter of a cycle of the line frequency. The frequency of the power waves is there again, twice the line frequency, okay? So as we look at one complete cycle, which would go here to here, again, we're seeing two of the power cycles. Power that surges back and forth like this, you give the power and the power is returned. You give the power and the power is returned. Power that surges back and forth in this manner is called reactive power. Reactive power from reactive components, and it's symbolized with the letter Q to distinguish it from, active power and other types of power. The reactive power in this figure 7.4 is given by the product of E times I. However, to distinguish this power from active power, we're not going to call it watts, but we're going to call it something called VAR, or volt amps reactive. We'll see kVAR, we'll also see megaVAR, but these are all ideas in terms of this reactive power. Now, there are measurement devices that can measure reactive power. Here's a VAR meter that would be made, this is 100 megaVAR, so this looks like some sort of power plant application here. But, it is designed to recognize, basically phase angles and quantify what the reactive power is. But a VAR meter measures reactive power. It measures the product of the effective line voltage times the effective line current times the sine theta, where the angle is it's the phase angle between E and I. And so a reading is only obtained when E and I are out of phase. Or in this case, if they were exactly in phase or 180 degrees out of phase, saying the same thing, then the VAR meter would read 0. So if this were a resistor connected here, a VAR meter would read 0. The dotted area under each pulse is the energy. The dotted area under each pulse is the energy in joules that's transported in one direction or the other. And clearly this energy is delivered as a continuous series of pulses of very short duration. Every positive pulse is followed by a negative pulse. The energy flow is back and forth, back and forth. Now, think about this for a second. What's the reason for these positive and negative energy surges? The energy flows back and forth because of the magnetic energy in the inductor that on the positive cycle is stored. Then on the negative cycle, the magnetic field is released. So there's a storing and a releasing, and a storing and a releasing. I love the analogy of, say, the idea of a starter. Of that inductor, it stores energy and boom, then it releases that energy. So when the power is positive, the field's building up inside the coil. A moment later, when the power is negative, the energy is delivered back to the source. We have an explanation for the brief negative power pole in figure 7.1. In effect, they represent magnetic energy previously stored in the motor windings that is returned to the source. So these little pulses that we saw way back here in figure 7.1, those were representative of the inductive part of that motor circuit. And every motor, every electrical machine requires a magnetic field that is usually done through an inductive element. And that's what that's showing now. Now, let me go off for just a brief second and I'll end this particular video. But think about it for a minute. Let's say you're the power company, right? And you went to all this trouble and you developed these or built these huge generation devices. And then you put up these power lines and built this infrastructure of transmission and distribution. And so here you have this huge generator and it's doing what it does, and it costs all this money to generate this power and get it out to the customer. And then the customer takes the power in, and then the customer turns the power back to the power company. Power company doesn't like that. The power company wants to charge you for the power. And if you're just borrowing it, and that's literally what you do, right? It comes and then you return, then they can't charge you for that, even though it costs them to generate, transmit, and distribute it to you. And so what we're going to find out is there's a way to measure the reactive parts of our power, and we will penalize you, says the power company, if you have too much reactive power or reactive components in your circuit. Okay, so let's wrap up 7.3.